Hello everyone, welcome back to the channel. Today's video will be covering the second half of Logic for Pure Maths Unit 1 students. Let's delve right in. So in front of me, I've placed 4 cards. And there's a rule governing these cards which says that on one side there's a number and on the other side there is an animal for each one of these cards. That rule is for sure known. And I have a second rule now. But this rule may or may not be true. On every side there is a 5, there will be a dog on the other side. In other words, if there is a 5 on one side of the card, then there is a dog on the other side of the card. Now the question, the task is, what is the minimum number of cards I will have to flip over to see if this rule is true? So you can stay till the end of the video and we'll use something called conditional logic to figure out whether or not the rule is broken if the answer doesn't come intuitively to you. Is it 1 card? Is it 2 cards? Etc. So what is conditional logic all about? In front of me there is what we would call a conditional logic statement. So essentially what it is it says if something X happens, then something X will happen, for sure. So in this case, we say if it rains, then the grass is wet. As usual, we can reduce this proposition down to mathematical form. And if we say it rains be proposition P, and the grass is wet is proposition Q, we can rewrite it in this form. So the if-then, in other words, the conditional part of this proposition is represented by an arrow. So this would be read as if P, then Q. So if P happens, then Q happens. That is what this proposition is all about. So what would the truth table for this P implies Q proposition look like? Well, firstly, let's examine the different possible scenarios. So firstly, if it rains and then the grass is wet, well, it would seem that this proposition is true. So what if it doesn't rain and the grass is still wet? Would this proposition still be true? Well, this proposition, firstly, only deals with if it rains. It doesn't matter if it did not rain. So even though it does not rain in this circumstance and the grass is still wet, we can say that this whole proposition is vacuously true. It's still true, but it's just vacuously true because this has absolutely nothing to do with this proposition. Because it could not rain and the grass could still be wet because another source could have wet the grass. Another possible circumstance is that it doesn't rain and the grass is not wet. This would similarly be vacuously true because, again, this proposition only deals with it raining. It doesn't say what should happen when it does not rain. So it does not rain and the grass is not wet. This proposition is still true because it could just be the case that there were no sources there to wet the grass. Now, if we say it does rain and the grass is not wet, i.e. P is 1 and Q is 0, this proposition is false if this happens because it essentially breaks the proposition because it goes against exactly what it says. This says if it rains the grass has to be wet, but in this case it rained and the grass is not wet, so we say that the proposition is false. So the truth table for an if-then proposition looks something like this. As usual, 0, 0, 0, 1, 1, 0, 1, 1, all possible combinations of P and Q. On the right-hand side, we have the output, P implies Q, or if P, then Q. And we see that the only time it is false is when P is true and Q is false. In other words, when the first thing, is true and this thing is false, because by definition, this statement here means that if this happens, then this happens. So if this does happen and this does not happen, then this whole thing is false, which is why when P is 1 and Q is 0, it's 0. In every other case, it will be true. And you can note that these are the vacuously trues because P is 0 in both of these cases. And this is also a truth down here. So let's take a look at another if-then or conditional logic proposition. If Trinidad is in the Caribbean, then 4 by 4 equals 16. So is this proposition true or is this proposition false? Well, we can go ahead and bring back the previous truth table. So this proposition will only be false when P is true and Q is false. Is that the case here? Well, Trinidad is in the Caribbean and 4 by 4 is equal to 16. So we know that this whole proposition is true. This will have a truth value of 1. So if this proposition said 4 by 4 was equal to, let's say not 16, but let's say 17 instead, would this proposition still be true? Well, in this case, Trinidad would be still in the Caribbean, of course, and 4 by 4 would be equal to 17, but this is not true. In other words, P is true, but Q is false. That gives us a truth value of 0, so this whole proposition here is false. Any other combination, like up here, say Trinidad was not in the Caribbean, or this proposition was Trinidad is in the Philippines, then 4 by 4 equals 16, it would still be true because this is false, but this is true. But as seen in the truth table, even when that happens, you have a truth value of 1. So, just like before, this is the truth table for the P implies Q. And 1, 1, 0, 1, when this is how the P and Q inputs are arranged, will always be the standard for P implies Q. Let's take a look at some definitions now for logic. So if P implies Q is called a conditional, something where you flip P and Q needs a name. We call that the converse in pure maths. So whenever you flip the conditional, that becomes the converse. So if you have P implies Q, the converse of this is Q implies P. There are two others. When you not both sides, you get not P implies not Q. That is called the inverse of this conditional statement. So the inverse of this is not P implies not Q. The contrapositive is when you flip both and you not both sides. So that would leave you with not Q implies not P. These are just standard definitions for conditional logic. So let's take a look at the truth tables for these different ones now. So 1101 is the standard for the conditional truth table. Looking at the converse, by saying Q implies P, this will only be false when the first one is true but the second one is false, i.e. when Q is 1 but P is 0. So Q is 1, P is 0, therefore the output Q implies P is 0. In every other case, it will be 1. For the inverse, you have to draw out not P and not Q afterwards, and then look at not P implies not Q. So when will this be false? This will be false when this is true, but this is false, when this is 1 and this is 0. So we look for that in this table, and we get 1, 0, therefore 0. And in every other case, it will be true. For the contrapositive, we have not Q implies not P, so this will only be false when not Q is true and not P is false, when this is 1 and this is 0. So not Q, 1, not P, 0, therefore this is false. And in every other case, it will be true. So these are the standard truth tables for the conditional, converse, inverse, and contrapositive. So if we take a closer look at these, we realize something interesting. The output column of the conditional is the same as the output column of the contrapositive, and the output column of the converse is the same as the output column of the inverse. So if we bring back what we had previously, when we said if it rains, then the grass is wet, we can realize some interesting things. So this is the proposition, if P then Q. The contrapositive to this is if not Q, then not P. Does that make sense in this case? So we say if the grass is not wet, then it did not rain. And indeed, that does make sense. So it turns out that when you have a true or correct conditional statement, the contrapositive will also be true. It'll make sense. Let's take a look at the converse of this. We say, if the grass is wet, then it must have rained. That does not logically follow, because if the grass is wet, there are many sources that could have wet the grass. And the same can be said for the inverse. So again, when you have a conditional that makes sense, the contrapositive will follow that same logic. The converse and the inverse will not. So if it's getting hard to follow along, it may be better if we try to use a diagram. So what does this diagram represent? Well, this basically represents all possible combinations of scenarios related to the if-then proposition we had before. If it rains, then it is wet. Because it can rain and it can be wet, it can rain and not be wet, it cannot rain, etc., etc. So let's take a look at P implies Q within this framework here. So what does P imply Q tell us when we're looking at this? So what this says is that if you are in P, in other words, if you are in this column, then you must be in this column in order for this to be true at least. You must be in this row if you are in this column. So we start off here and we say, oop, we have to be here. So we can say that it is true here. Now, this will be broken if you go in this column and you end up down here. So we say that this will be false. Now this tells us absolutely nothing about what's supposed to happen in this column, which is why we say that they end up being vacuously true. Similarly, with the contrapositive, this tells us if we are in this row, we have to be in this square. If we are in not Q, we have to be in not P as well. So that tells us that if we are here, when we are in this row, this proposition is broken, i.e. truth value is false. And as before, this proposition tells us nothing, no rules about what should happen up here, so these are also given the truth. And that is a sort of visual understanding of why these two propositions can be equal to each other. Okay, so let's take a look at the converse now, which is Q implies P. Now, what does this tell us? This tells us that if we are in this row, we have to be in this square. In other words, if it is wet, then it has to rain. And so it is true in this square here. If we were in this row and we ended up here, therefore, this would be false. So Q implies P ends up having this as the layout. Whereas before, with P implies Q, these two were switched. When we have Q implies P, it switches these two here. And similarly, with the inverse, this tells us that when we are in not P, we have to be in not Q. So if we are here, we have to be in not Q down here to make this true. If we are up here, it is false. And that also shows us why these two are logically equivalent to each other. Let's go back to the original conditional that we had before. P implies Q. Now that looked something like this. So we can take a look and examine another way to interpret what's going on here. So what is this telling us? This is telling us that if it does not rain, this will be true. And if it rains, well, if it is wet, then this will be true. There's a sort of overlap in it being wet and it not raining to give this a whole truth value of 1. In other words, we can rephrase this. So instead of saying P implies Q here, this is seen to be logically equivalent to something else because we have other propositions in here. We have it is wet and it does not rain. In this case, this would be not P because that's where it's true, or Q. So in other words, by saying if it rains, then it is wet, that is logically equivalent to saying it either does not rain or it is wet. And you can make sense of that using this, because this will be true when it does not rain or it is wet. There is an overlap, which, as seen before, or allows for, because if this is 1 and this is 1, this whole thing is also given a truth value of 1. So that is a rule that most students need to use whenever you reduce complex propositions down. So again, P implies Q is the same as saying either not P or Q happens. So now let's quickly go over some examples. But before we do that, let's take a look at one more thing called the biconditional in logic. Now the biconditional says that P implies Q, but that Q also implies P in itself. So what that tells us is that these two are basically sort of in sync. So whatever P is, Q has to be, and whatever Q is, P has to be. It goes both ways now. So that means that if P is 0 and Q is 0, this biconditional is true. If P is 1 and Q is 1, this biconditional is also true. But if these are different, then this biconditional is said to be false. So this would be the truth table of that biconditional. So if we look at this example, 2 plus 2 equals 4 if and only if 5 by 5 equals 25. This here, if and only if, is another way to represent this. So we can say 2 plus 2 equals 4 if and only if 5 by 5 equals 25. This is a correct or a true biconditional because this has a truth value of 1, 2 plus 2 is equal to 4, and 5 by 5 is equal to 25. What about this biconditional down here? This says 5 by 5 equals 20 if and only if 2 by 2 equals 4. Now, 2 by 2 is equal to 4. This does have a truth value of 1. But this has a truth value of 0 because obviously 5 by 5 equals 25. And because they have two different truth values, the biconditional is said to be false. Also, two important things to note. There are special terms in logic called a tautology and a contradiction. A tautology, an example of that, is P or not P. And essentially what a tautology is a statement that is always true. In other words, it always has a truth value of 1. That makes sense if you think about it, because if I were to tell you, either I eat ice cream or I do not eat ice cream, well, I'm basically not telling you anything, but I'm still correct because I can be eating ice cream or I cannot be eating ice cream. So, a tautology, again, whenever you have a truth value of 1 or all 1s in the final column, that is a tautology because the statement is seen to be always true, no matter the truth values of the individual propositions making it up. A contradiction now is sort of like the opposite. It's always zero. It's always incorrect, as the final column in the truth table will be full of zeros, always have zeros. And an example of that is P and not P. So for example, if I say I eat ice cream and I do not eat ice cream, that's obviously a contradiction. That statement has to be false because I cannot be doing one thing and I say I'm not doing that thing. It would make no sense, so the truth value of contradiction is always zero. Okay, and lastly, we're going to take a look at an example. So let's suppose we have to see whether this proposition here, this compound proposition, is a contradiction. And to do that, we need to see if the final column will be all zeros. So let's take a look at this truth table. So we have every possible element of this whole compound proposition X. This is P or not Q, as here, not P and Q, and then of course we have not P and not Q in separate columns. So as usual, we start off with 0, 0, 0, 1, 1, 0, 1, 1. So now we can write not P as 1, 1, 0, 0, because it's not this, and then not Q as 1, 0, 1, 0. And that means that if we take a look at P or not Q, we have to look at this and this. So P or not Q, that's a 0 and a 1, which will give you a 1, 0 and a 0, which will give you a 0, 1 and a 1, which will give you a 1, and 1 and a 0, which will give you a 1 as well. Now we have not P and Q. So that is this and this. And now we're applying and. We're not using or anymore. So not P and Q. 1 and a 0 will give you a 0. 1 and a 1 will give you a 1. 0 and a 0 will give you a 0. And a 0 and a 1 will also give you a 0 because it is and. And lastly, we take these two things and we use the function and we say that 1 and a 0 gives you a 0, 0 and a 1 gives you a 0, and these are also zeros down here. So overall, this whole thing up here is proven to be a contradiction because every single output is 0. In other words, for any value of P and Q, the output will be 0, and this compound proposition will be false. So now we go back to the original example. We have these 4 cards, and we need to see if the rule is broken. And that rule is behind every 5 there is a dog. In other words, if there is a 5 on one side, then there is a dog on the other side. So of course we need to check this and see if the rule is broken. Now it says that there is a cat, so that means that the rule is broken. Do we need to turn over this card? Well, the rule never said if there is a dog there is a 5. That would be in this case the converse. So we don't need to regard that. This we do need to turn over because the contrapositive says that if there is not a dog, i.e. there's a cat, there cannot be a 5 on the other side. So we have to turn this over, and well, there is a 5. So again, the rule is broken. Do we need to turn over the 3 now? The rule never said that this would be the inverse. If there is not a 5 on one side, then there is not a dog on the other side. The initial rule never said that when you turned over a dog, you couldn't have, when you turned over a 3, you couldn't have a dog. So it doesn't matter whether we turn this over or not, the rule will not be broken no matter what this is. So now, because of conditional logic, we know that we only have to turn over 5 and cat to see if the rule is fulfilled. Okay, thank you all very much for watching.